In this video, we're discussing the symmetric equation of a line versus the parametric equations of a line. We've already talked about parametric equations, but I'd like you to be able to convert from parametric equations to symmetric equations easily, and vice versa. And I'd also like you to be able to look at either form of the equation of a line and identify both a point on the line and a direction vector for a line. So just as a quick review, if we have a line that passes through the point x naught, y naught, z naught, and has direction vector v with components a, b, and c, the parametric equations of the line look like this. And when t equals 0, x, y, and z are equal to x naught, y naught, and z naught. When t equals 1, it's as if we've started here, and then we've gone maybe like 1 unit of time later, we've followed this vector, and we ended up over here. We end up at x naught plus a, y naught plus b, z naught plus c. If t equals 2, we'd travel along this vector twice on this line, and so on. If t is negative, we get all the points on this side. And of course, t doesn't have to be an integer. T could take on any value. So if t was 1/2, we'd go like half of a, half of b, and half of c units in the x, y, and z directions respectively. Okay, so those are called parametric equations of the line. I think most of us are pretty comfortable with that because we can think of t as a parameter representing time. And as t takes on all values, you get the whole line. So maybe there's a particle at t equals 0, it's here. At t equals 1, it's here. At t equals 2, it's there. At t equals -1, it's there, and so on. Now, if I take these equations and I solve for the parameter t, and I don't write x of t, but I just write x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. If I take each of these equations and solve for t, well, the t on this line, or the t in this equation, is the same as the t in this equation, which is the same as the t in this equation. So we can set all of those equal to each other, and we get what are called the symmetric equations of a line. So if I take this and I solve for t by subtracting x naught from both sides and dividing by a, I get x minus x naught over a is equal to t. And if I do the same thing here, solving for t, I get y minus y naught, and then divide by b, that would be equal to t. And I can do the same thing here. I've got z minus z naught, and we divide by c. And this is what is called a symmetric equation of a line. Sometimes people call them symmetric equations of a line. And I guess there's more than one equation implied there with the two equal signs. And normally this part's not written, but I like to write it for myself to remind me where this comes from. This is just taking each of these parametric equations and solving for t. So these are called the symmetric equations, or a symmetric equation of a line. Now, being familiar with both is important, and the standard form of both of these is important, because once you understand what the form is, you can quickly identify that direction vector v and x naught, y naught, z naught. So let's look at an example. If I have x equals 1 minus 2t, y equals 3 plus 5t, and z equals t minus 4, those are parametric equations of a line. If I take this and I solve for t, I'll have x minus 1 divided by -2 is equal to t. Over here, I'll have y minus 3. Then I divide by 5, that's equal to t. And over here, careful, these are in a different order. If I'm solving for t, I get z plus 4 is equal to t. So these parametric equations correspond to that symmetric equation. And if you're wondering, okay, how can I identify that point on the line and that direction vector of the line? Remember, the point comes from setting t equal to 0. So when t is 0, x equals 1, y equals 3, and z equals -4. So x naught, y naught, z naught is 1, 3, -4. Now notice over here, your x naught, y naught, z naught, they appear in the numerator. X naught, y naught, and z naught are the numbers that you're subtracting from the x, the y, and the z. So if you see a -1 here, x naught actually is a +1. X naught's going to have the opposite sign because of the negative in that equation. So from here, if I want to identify x naught, y naught, and z naught, I just look at the numerator. I have x naught is 1, y naught is 3, and z naught is -4 because we have the opposite sign. It's the same thing that we had there. Now to find the direction vector, if you have parametric equations of the line, you just look at the coefficients of t. Oops, not the t itself, but the coefficient of t. The direction vector, if we're in 3 space, has components a, b, and c. That's going to be -2, 5, and +1 in this case. Similarly, over here, a, b, and c appear in the denominator because these coefficients of t appeared in the denominator when we were solving for t. So this is my a, b, and c, the components of the direction vector of a line when you're given the equation in symmetric form. So I'd like you to be able to go from this to this, and then be able to look at this and identify the point and the direction vector, and to be able to look at that and identify the point and the direction vector. So let's say you're given this line. Well, first of all, I notice that there's nothing under the y, almost. It's an implied 1. So from this, I look at the denominator, the 2, the 1, and the 5 are there. So my direction vector is 2, 1, 5. And the point P comes from whatever you're subtracting from the x, the y, and the z. So we're subtracting 3, we're subtracting nothing, and we're subtracting a 1. So the point P is 3, 0, 1. So when I see this, I think of this, or even better, I think of this. This is a line that passes through 3, 0, 1, and it has a direction vector. You can start anywhere. I'll just start there. It has direction vector with coordinates. Nope, components. Sorry, did it again. Components 2, 1, and 5. And then if I want to get the parametric equations of this line, I set each of these expressions equal to t and just solve for x, y, and z. So if I have x minus 3 over 2 equals t, multiply both sides by 2, add 3 to both sides, and you get that. And then we have y equals t, not much to do there. And then we have z minus 1 over 5 equals t, multiply both sides by 5, and then add 1 to both sides, and you get this. And then you see again, x naught, y naught, z naught is 3, 0, and 1. And the components of the direction vector are the coefficients of t, so 2, 1, and 5, which is exactly what we had there.